Okay, so today is Monday, February 22nd. Quiz number 3 is due, should be in the folders. Today we're covering a technique called partial fractions. This is yet another integration technique. Our most powerful one was U substitution. Last class we learned something called integration by parts. Today a brand new technique which will allow us to solve a new class of integrals. Coming up on Wednesday, the third project is due. This one is just all about areas. You're welcome to work with each other and work with random folks on the internet and work with Math Studio helpers and anybody you want to on that project. That project is due on Wednesday. Wednesday is our review day for test number 1. At the end of today, we'll be finished with the material for test number 1. It will be on everything we've covered up to and including today's stuff, 10 lessons. And then our first test is on Friday, February 26th. It is not too early to start studying for that test. As you study for that test, know that you can bring in a one-page reference sheet of your own creation, 8.5 by 11, front and back. Anything you want to write on there, you can write on there. Just don't photocopy somebody else's stuff. And you can start doing that today. Making that reference sheet is part of a balanced study plan. Rob? It doesn't have to be handwritten. I just don't want it to be photocopied of anybody's stuff. Yeah. I have no idea. It's written to be an hour. Some people will finish in less than that, but it's written to be an hour. Yes. The answer key for quiz 2. Oh. No, but the other thing, you can't photocopy the answer key for quiz 2, but you can bring with you the reference sheet that's at the front of this packet. Somebody find it. What page is that on? No, it's not that.
The answer sheet. That's
What's the?
Page 5.
Yeah, page 5. So you can bring in your own reference sheet and page 5 of the packet, which has not all of the stuff on that quiz, but a bunch of it. Okay. And on the back of this page 5 is the U substitution walkthrough. So you'll have both of those.
So those are additional.
Yeah, you're gonna have 2 pages. Page 5, which you'll rip off, and then your own page. Good. Other questions? Okay. So let's jump in on the top of page 80.
Oh, wait, actually, I have one more question.
Yanni.
Can we bring a scientific calculator?
Yes.
Okay.
Yeah. Yes, scientific calculator, no to a graphing calculator, no to a cell phone. I will have calculators to loan if you don't have a scientific calculator. So that means, I'm not going to ask you to graph some crazy thing because I know that you can't do that with just a scientific calculator. Sam? I don't know. What's 7.3? We'll look it up and we'll figure out why we're skipping it. Okay. All right, here we go. In this class, we learn a new technique for integration called partial fractions. Every problem that we do today is going to have to do with fractions. So that's good news for some of you and very bad news for others of you who just despise fractions. I will say that that we're going to be spending a lot of time today doing algebraic fractions. That is fractions with x's in them and adding them and subtracting them and multiplying and all of that good stuff. So hopefully it will come back to you if you haven't played with this kind of fraction stuff in a while. All right, so we're going to find the value of this integral right here, 5x minus 10 over x squared minus 3x minus 4. There is a natural choice for you. You don't need to write this because it isn't going to work, but when you have a fraction, what's a natural? Is the denominator, right? So we let u equal the denominator, and then we take a derivative. And we hope it looks an awful lot like what else is in the fraction. And unfortunately, we can't do anything to 2x minus 3. Like, we can't multiply it by some magic number to turn it into the 5x minus 10. It's just not going to work. Things will not cancel. So our only natural U substitution doesn't work, so we need a new technique, and here it is. First thing we're going to do is, I'll call that guy I again. First thing we're going to do is factor the denominator. So 2 sets of parentheses. What do we get when we factor this one? X minus 4 and x plus 1. Okay. And then we're going to rewrite the integrand like so. We're going to copy the 5x minus 10 over this factored version. And we're going to rewrite it this way. We're going to write it as some number called a divided by the first factor in the bottom, x minus 4, plus some number, we'll call it b, over the second factor in the bottom.
So it doesn't matter that we take the integral signs out?
I'm intentionally taking the integral sign out temporarily because we're going to be doing just an algebra technique here, and then we'll come back to the calculus integral piece after we're done with the algebra. Yeah. Okay, let's see if we believe that such numbers a and b exist to make these two things equal. Well, let's see. What would the lowest common denominator be when you add these two fractions? Right, we're adding fractions, so we need a common denominator. These
minus 3x minus 4.
Yeah. I mean, like these two denominators have nothing in common, right? So the least common denominator is just going to be multiplying them together. In some sense, it's the worst possible case. And multiplying them together is exactly where we came from. So at the very least, I expect that kind of that denominator. And we'll do the algebra in just a moment, but so don't write this here. But what would I need to multiply this by to turn it into the right denominator? X plus 1, but you can't go around multiplying the bottom of a fraction by x plus 1 without multiplying the top by x plus 1 as well, right? Well, you know what, we can squeeze it in here. Go ahead and write that down. That's the technique, right, is we're going to multiply top and bottom by x plus 1. And so upstairs, I'm going to have a constant times x plus a constant times 1, like distributing that a, and that looks kind of like what I have over there on the top. So maybe I'll be able to choose a and b suitably so that we'll get a 5x minus 10. And then we'll play the same game here. What do we need to multiply this by? It's x minus 4. And therefore, right away, multiply the top by x minus 4. Okay. So the next step is going to make some of you very happy because we're about to get rid of all the fractions. If we multiply both sides by x minus 4 times x plus 1, then all of these denominators just cancel out, yes? Okay, so then we'll copy down what's left. 5x minus 10 equals a times x plus 1 plus b times x minus 4. Right, we built all the denominators to be the same, and now they're irrelevant. If the denominators in that equation match up exactly, then the numerators have to match exactly. Okay, now the goal is to find a and b to make this equation true. Now there's two choices. One choice involves picking any numbers that you want for x. Pick some values for x. This equation is supposed to be true for any x at all. So for example, if I pick x equals 17, I could write down, let's see, 5 times 17, that's 85. 85 minus 10 is 75, is equal to 18a plus 13b. That's an equation that has to be true. But goodness, we could do better than picking x equals 17. If you pick x equals 1, you'll get smaller numbers, even better. If you pick x equals 0, you will still get small numbers, even better. 2 is okay. I do like the idea of making some parts of this equal, some part equal to 0. That's the trick right there. If we use x equals 4, then the part with the b in it completely vanishes, which is much better. Don't write this, but the equation that I quoted to you was something like, I don't know, 18a plus, I'm going to say 13b. I picked x equals 17, which was not the best choice because I get this equation. It's okay, but wouldn't it be so much better if we just didn't have the b in the equation? Okay, so we're going to choose what Mario said, which was x equals 4. And so we're going to plug x equals 4 in everywhere in this equation. So the left-hand side, 5 times 4 minus 10 is 10, equals, what's in the parentheses? 5. So 5 times a plus 0 times b. That was why 4 was a good thing to pick, because now it's obvious what the value of a is, right? It's 2. A is 2. Mario said it, but let's get somebody else. What's another good choice for x? -1. That's the other winner. So plug -1 in for all those x's in that bottom red equation. So what do we get there? -15 equals 0 times a, and then minus 5b. All right. So b is 3. Okay, so we've got our a and b. The algebra part is done. We actually haven't done any calculus to this point, right? This has all been algebra and had nothing to do with finding an antiderivative. So we're going to come back to the antiderivative, but I want to say that this problem right here is the simplest flavor. We'll see more complicated ones in just a minute. And for the more complicated ones, pretty much for anything other than this simplest kind of problem that we're going to do today, picking values of x is not necessarily the easiest way to solve for the unknowns, a and b in this case. And so I just want to show you here, even though we've already found a and b, I just want to show you an alternate, which is like a tiny bit more work for this particular problem, but less work for like all the harder problems than this one. So here's another option. Go back to that red equation, and let's go ahead and distribute the a and the b. So we go 5x minus 10 equals ax plus a plus bx minus 4b. And then we're going to recombine or regroup the terms on the right-hand side so that the x's are all together. So what's touching an x on the right-hand side? A plus b, right? And so I can factor the x out of those two terms. And then the other terms don't have any x's in them, so we'll just copy them. I'll put, it's kind of silly, I'll put a 1 times. This is just an alternative to what we did here in black, just a completely different way to find the a and the b. So it's kind of silly because we already know the answers are 2 and 3, but I want to show you an alternative that will be, yeah, that's the a and the 4b that don't have any x's on them. And I didn't do anything by factoring out the 1, but I'm just kind of laying it out in similar terms where it's like, all right, you got your x terms, and then you got your 1 terms, and in another problem there might be x squared terms. So it's really just like line up the x's and then factor out whatever you can. And so, hey, look, if these two sides are supposed to be equal for every value of x, then the value of this a plus b has to be 5, because those are both the things that are touching the x. Right? The left-hand side is 5x minus 10. Well, the right-hand side has to also be 5x minus 10. So the thing in that first parentheses that I just highlighted, what does it have to be? It's got to be 5. You buy that? And what does the thing in the second parentheses have to be? This thing here has to be -10, right? I mean, they're both 5x minus 10. So because the right-hand side is grouped so that it's just the x times whatever and then the constant times whatever, essentially we're matching up coefficients. This part right here is probably something that many of you have never done before, like take two polynomials that are equal and match up their coefficients. But I want you to buy that it's true. I mean, if these guys are equal as polynomials, meaning for every value of x, then the coefficient of x on the one side has to be the same as the coefficient of x on the other side. And so we get our two equations. The yellow highlighted is 5 equals a plus b. And the green highlighted, -10 equals a minus 4b. This should look familiar, right? You guys have done 100 examples of solving 2 equations and 2 unknowns. So you've got your techniques. Standard ones are substitution and elimination. Let's at least just verify that the answers we got satisfy this, like that you would get the same 2 and 3 if you solve this the rest of the way. A plus b, is it 5? Yeah, right, it's 2 and 3, okay. And then a minus 4b, let's see, 2 minus 4 of those, 2 minus 12, -10. So you would get 2 and 3 by solving it this way. Like I said, the right-hand way is more work in this particular example, but for many other examples, the right-hand side will be less work than the left-hand side. Okay, so what does any of this have to do with calculus? Well, let's say I kind of run out of space here. But let's go back. So this is now out of order, but we're going to go back up here to the top. Yeah, this is good here. Equals integral. So what we discovered was that a was how much? 2? So 2 over x minus 4 plus, and then b was 3 over x plus 1. So the very first equation that we wrote here in red, before we started putting the blue stuff in, the first equation in red is all that I've copied down. The original 5x minus 10 over that denominator, that's what we had to start with. We said, hey, it's equal to a over x minus 4 plus b over x plus 1. A over x minus 4 plus b over x plus 1, right? That's what we discovered. So with those choices of a and b, we've rewritten our integrand as the sum of these two fractions. We still haven't done any calculus. But now finally, after all of that algebra and pre-calculus stuff, we're ready to do some integrals. Integral of 2 over x minus 4, it's a u substitution. What would you let u equal? X minus 4. And what's the derivative? 1, which we can work with, right? And so that guy is going to turn into something very close to 1 over u du. So what kind of antiderivative will it have? A natural log. And the 3 over x plus 1 will also be a natural log. Right? So we took the complicated looking denominator that we had before. It was a quadratic with the x squared. Split it into 2 linear denominators. And hey, easy u substitutions. So I'm going to put ... where you do the u substitution work. We'll just write the answer here. It's 2 ln of x minus 4 plus 3 ln of x plus 1. So that's the final answer there. Stunned silence from the room. What's wrong with the x minus 4? Yeah, 2 separate u substitutions. Yeah, because in your mind, you're 2 different integrals is what you're imagining.
Okay.
Yeah. Yeah. Okay. So I'm going to put a damper on your spirits, but like I said, this is the easiest kind of partial fractions one. So let's take a look down below. All right. So depending on the way the denominator looks, you're going to set up the fractions on the right-hand side differently. So if the bottom has a factor of the form x minus a number, which we had twice, right? We had x minus, what did we have? X minus x plus 1 and x minus 4, right? Then you put a constant on top of that factor. A over x plus 1, b over x minus 4. If there were a third one, you'd put another one, c over that third guy, all right? So if you just have a linear factor, single linear factor, you just put a letter on top of it. This is a little bit different, this x minus c to the n. This is saying you have the same factor repeated, like x plus 1, the whole thing squared. You don't put an a over x plus 1 and a b over x plus 1. That's not going to cut it. It turns out you need to put a constant on top of each increasing power of that factor, starting at the first power. So for example, if you had a 3x minus 5 over x plus 2, let's do squared. You would split this guy up as an a over what? X plus 2. You start with the first power always, plus b over x plus 2 squared. If it had been cubed, you'd have a c over the thing cubed. You start with the first power and you build all the way up to the highest power. Mario. Then it would be the same idea as up above. You'd put a constant over the first power and then a constant over the squared and a constant over the cubed all the way to the end. I would never be so mean as to give you. Yeah, Rob. I like using separate letters, and I think it's easier to use separate letters, A, B, C, but in the notes, The only reason it's written with subscripts there is so that we can write it in general. Like I can't say a plus b plus c without knowing how many you have. And since the number we have is n, we're just trying to, yeah. Okay. All right, and then the last kind of thing is where instead of having a linear factor, right, the power on these x's here is 1. If you have an irreducible quadratic, meaning a quadratic that you couldn't factor, we could factor this thing, right? What was the original problem? X squared minus 3x minus 4. We could factor that, but there's a decent chance we couldn't have factored that. And if you can't factor it, then you end up putting something like ax plus b on the top, which is a very different kind of creature than just a constant. It's a constant times x plus another constant. So let's see if we can put it all together in one crazy example. So take a look at this thing down here. I see an x minus 1. I see an x plus 1 squared. And then I see an x squared plus 4. It's already been factored. We just have to look at the forms of those denominators, or of the things in the denominators. X minus 1, what do we put on top? Just an a. That's the simplest case, and so I'm going to highlight, highlight in yellow. This guy is the only term that the x minus 1 requires. The next guy, though, is an x plus 1 squared. It's linear, but it is squared. And so this was the part where you have the first power of the thing and the second power of the thing, and if we needed a third power of the thing. So there's the first power of the thing. There's the second power of the thing. And we stopped. Okay? And the last thing, x squared plus 4, we can't factor that, right? It's not x plus 2 times x plus 2. Make sure you don't think it is. And so when you can't factor it, you end up putting the linear thing up on the top, bx plus e. So that would be the way we would write out the decomposition. Yes? Yes. Yeah. Yeah, so this is just part, it's in the table up here, but this is just part of what we need to apply when we see a repeated linear factor. So you see an x plus 1 with a power on it, you have to write the x plus 1 by itself, you have to write the x plus 1 squared, maybe x plus 1 cubed. You got to go all the way up from the first power on x plus 1 all the way up until you get to the actual power in the problem. Chris. Right, okay, so it's, okay, so I think what you're saying is that you want to know why we need why we need this power, the x plus 1 squared. Right, because this is x plus 1, x plus 1. Right, so suppose that I asked you, we know we're trying to build this crazy denominator from the beginning, right? The denominator is supposed to look like x minus 1, x plus 1 squared, x squared plus 4, right? Suppose that we looked at your idea, which is a good one here, and we said, hey, we're going to smush these together and make a single fraction. What would the denominator be? It would just be x plus 1, right? If you just added these two guys, your two fractions, your denominator isn't rich enough to get us the thing that we want. So for sure, we got to have a squared on one of these guys. I can't really talk about why do we even need two of them? Like, can't we just get away with having one of them? It turns out you're not giving yourself enough freedom to make sure that it's possible to find a, b, c, d to make the top match this 2x cubed minus x squared plus 3. That's kind of a hand wavy thing. But for sure, we got to have the x plus 1 squared to get that denominator. What's that? Yeah, it just wouldn't work out. You wouldn't get that denominator if you didn't have this squared thing here. Trevor? So the bottom row in this table is only good for things that are irreducible. So if you can factor the thing, you have to. Yeah. Okay, lots of good questions. Let's take a look at number 3. We're not going to do this full one out, but we are going to set it up together. I'm going to copy the integrand. I think this is worth writing without the integral symbol. So go ahead and copy the integrand. Okay, and we're going to try to set this thing up. The x squared plus 1 is not the first thing I would deal with. I see the x minus 2 is the simpler thing. So what do we do with the x minus 2? A, great. Single linear factor, easiest thing we could have. Can you factor x squared plus 1 into two sets of parentheses? The answer is no. So this is the bottom row of the table where it's an irreducible, meaning not factorable quadratic. So what goes on top of such things? Bx plus c. That's it. Now you're going to have a chance in the activity to finish this kind of a problem. There's another one that's very similar to this one. So we're not going to finish this one now. Like the algebra is involved, and I don't want us to spend, I don't want you to just watch me doing the algebra. I want you to try it in the activity in a couple of minutes. But I do want to give you a hint when we actually, like after you have found the a, b, and c, like how to actually handle the integral. So we're expecting to get two different integrals to deal with. So I've already written the answer down here. You can copy it if you want, but you don't need to. But this is what you get after you find the a, b, and c. It turns into this simpler sum of two fractions. And even after all of the algebra, which we just skipped, there's still a bunch of work to do. This integral right here, what is it? It's like a 1 over u, right? It's another u substitution. So what is this integral going to lead to after the u substitution? There's another natural log. So this one is going to be natural log of x minus 2. There is a u substitution that we're not showing any of the work on. Do it all out. Take your time. But the first guy is still a little bit of a bear. X plus 1 over x squared plus 1. Yeah, if you do a u substitution and let u equal to x squared plus 1, then you're expecting a 2x. We have an x, but this plus 1 is an issue. And so the thing you have to do is split this guy up into two different things. X over x squared plus 1 plus 1 over x squared plus 1. By that's equal to the original fraction. If you do the integral of the second thing, hey, that's on our table. What is it? That's arctan. Excellent. Doing the integral of the first guy, the u substitution will work now. If you let u equal the bottom, the derivative is 2x, which looks an awful lot like what's sitting here. So this is almost going to be a 1 over u du. There'll be a 2 floating around someplace that you have to fix, okay? All right. So I know that this is not easy. So take your time. Lots of fractions. Most of what you're going to be doing today is algebra. It's only a little bit of calculus at the very end of doing lots of fraction algebra. I want you to change the order in which you tackle the activities today. Here's the new order. Starting with 3A, jumping to 2, 1B, 1A, 1C, and 3B if you have time to get there. And when you get to 1A, you're going to fix these two things I've crossed off in red in the answer key. Okay? So let's follow that order.
Start with
3A. Okay, start there.